When you have an input array which is almost sorted and you want to sort the elements, the best sorting algorithm you can think of is insertion sort. It is the most commonly used sorting algorithm. In this tutorial, we will learn about each and everything that is there in insertion sort along with algorithm, its implementation, number of comparisons that are there, number of swaps, and all those things. Before we get started, I want you to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new updates on video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on this video any queries or suggestions, and I will respond to your comments. What is insertion sort? So the question is that what is sorting? So you might be thinking, why do we need these sorting algorithms? So if I told you that you have a bunch of students, right? You have a bunch of students and they each have their roll number. They are not present in in a numerical order, or you can say they are not present in some order. I want that order to be maintained. Let's suppose you have 1 to 10 students in those bunch of students, and each are having roll numbers from this range, from 1 to 10. Now, some of them are absent and some of the roll numbers have left the school, but the roll numbers are not changed yet. Now, what I told you, please sort them or arrange them in such a manner so that I can easily understand which roll number is after which, either in ascending or in descending order. Let's suppose 1 is there, 2 is there, then 6 is there, then 8 is there, then 10 is there. So rest of the roll numbers I can easily depict, okay, these are the ones which either are not there or are absent. So in order to do so, we have these sorting algorithms in picture. And one of those sorting algorithms is insertion sort. Now, it is the simplest, easiest, and a brute force sorting algorithm. Now, what do you mean by brute force? Brute force means straightforward, right? In a naive way, it means straightforward. That means you're not you're not considering any efficiency, or you don't care about time complexity or space complexity. You just straight away sort it with the most simpler and naive approach. Okay. In this brute force algorithm, what happens that let me give you an example, right? Obviously, we can sort with the help of this insertion sort algorithm. You can obviously sort either in ascending or in descending order, right? Let's take one example. We all know about the card game, right? Wherein you have a bunch of cards, right? Suppose you have a single card that is in your hand, right? And you have a bunch of cards available on the table. Now you start picking those cards one by one. Obviously, the one that is in your hand is sorted, because if I told you to sort a number 1, obviously there is only one element in the array or anything, right? In the linked list, I told you to sort it. But if you're having only one element, that is itself sorted, right? You don't need to sort that. Similarly, what happens now, this card is in your hand, right? It's just like playing cards, right? Now you have this one card in your hand and it is obviously sorted. Now what you will do in the next turn, you start picking up one by one from these set of cards that are available on the table. Now let's suppose this is 0. Okay, I'm considering these numerical values so that you can understand and you can just connect the dots, right? So what happens, you have the 0 and now you start comparing it. Now we are considering the scenario where you are trying to sort in ascending order. Okay, so now let's try to erase these things so that it's easier for you to understand things. Okay, so now you have these two elements, right? And now we are considering the case wherein you are trying to sort in ascending. So you check, okay, if 0 is less than 1, yes it is. Now you swap them, okay? Now you have 0 and 1. Now these are the two cards that are present and both of these are sorted. So now insertion sort works in such a manner that you will always have two parts, right? One is the sorted part, obviously, which is in your hand, and one is the unsorted part, which is on this deck, right? So similarly, you will start picking elements, or you can start picking these cards one by one and keep sorting them. Okay. Now this is one simple scenario wherein you can apply what insertion sort. Right. This is the most simpler way one can explain or one can understand you this insertion sort algorithm. Now it is simple, right? Now you start picking these elements and you keep sorting them, and at the end, when all of these elements are exhausted, you will get your sorted array. Now let's try to understand insertion sort algorithm. So in this algorithm, what happens? Obviously, now we know that we will have two parts, right? One is the sorted part and another is the unsorted part, right? So obviously, the one element that is present in your hand, or the element or the card that is in your hand, and there's only one element there, right? The one element in your hand, obviously that is sorted, right? So we will not consider that first element, and we will start our iteration from the second element, right? Now we understand why we are doing this, that we are starting from 2 to n minus 1 or 2 to n, depending upon the array that we are starting from. Either we can start from 0 index or we can start from 1 index, right? So we always start from element number 2, right? And then what we will do, we'll just store this value inside some temporary variable, and then we will check if that element is less than the element that we have in this sorted part. If that is the case, then we will shift their positions, right? And we will get both. Now we will have two elements in the picture, that is 0 and 1, and both of these will be sorted in ascending order. And then what we will do, we'll consider the rest of the cases, that is starting from 3 to so on to n. Okay, now you might be thinking, okay, how does this thing happen? Let me take an example and let me show you how. Let's consider this array that we have over here, that is index 0. These are all the indexes that we have, and this is our array, that is 23, 10, 16, 11 and 20. So in the first step, we are making partitions. Now this is our sorted part, that is the first element, and this is our unsorted part. Now what we will do in the first iteration, this is our iteration number 1, because this is the case wherein we will start moving from second index, that is first index, if we consider from 0, right? So we consider from second element and so on to n, right? So now in the first iteration, what we will do, we'll compare these two values. Okay, let me just erase everything so that it's easier for you guys. So now we will compare these two. Now obviously 10 is less than 23. What we will do, we'll shift their positions. Now this is your sorted part and this is your unsorted part. Again we will do the same thing, right? So in second iteration, what we will do, here comes 16. Now what we will do, we'll compare it first with 23. Okay, we know now, okay, 16 is less than 23. So now what we will do, we'll swap their positions. So this is 16 and this is 23. Now what will happen? Now 16 will be compared with 10. Obviously it is not less than 10, so it will remain as at its own position, that is its new position at index 1, right? So this is the second iteration, and after second iteration, this will be your sorted part. As you can see that I have bolded this text, right? Bolded the borders of these two elements, and bolded the same for these three elements, because this is the sorted part that we have over here, and this is the unsorted part. Now what will happen in the third iteration, that it will check for this number that was there, it is 11. So for 11, what we will do, we'll compare it with what, read this thing. Now we'll take 11 into consideration, and now we'll check it, we'll swap them, then 11 is here, 23 is here, we'll check them, we'll swap them, 16 is here, 11 is here, we check them. So since 10 is less than 11, so nothing will happen. So in the third iteration, what will happen? We will have 10, 11, 16 and 23. These are all sorted, and we are only left with one element which is unsorted, right? Now in the final iteration, what will happen, that 23. Now this 20 will be at its original position, that is here, and rest of the elements will be sorted. Now since we have exhausted all the elements have been exhausted, and we at the final step, that is in iteration 4, we will have this array that is sorted. Now let's try to understand insertion sort implementation. So consider this function which is written in C. Now let's see what happens in this function. So in this function, that is insertion sort, we have two arguments, that is the elements in the array, that is our array, and the size of the array. Now let's clear this thing and let's see. Let's take an example, a simple example, that is 10, 5, 6, and 20. In this we have these indexes. Now this is the name of the array, that is ARR, we have passed in this function. Now what is this n? This is nothing but size of this array, which is nothing but 4. Now we have already seen the algorithm wherein we always talked about two portions, that is the sorted part and the unsorted part. Now we know that the first element is sorted in itself, and this is our unsorted part. So that is for the same reason we are starting our iteration from 1, that is this index. Now let's try to erase this thing and let's see what are the pointers, what are the iterators and variables that we have used. So let me clear out this thing, and we all know now this sorted part and unsorted part. Now let's see what are our iterators. So we have our j pointing to this index, that is ji minus 1, and we have our I which is pointing to this element. We also have a temporary variable which I will tell you, that is tmp. Just a minute. Okay, so we have 10, 5, 6, and 20. This is our j, this is our I, these are our indexes, and this is our tmp temporary variable, which is right now 5. Now let's talk about the first iteration. What happens in that first iteration? We are over here. We talked about these pointers, right? Now we are checking if j is greater than 0. Yes, it is. It is greater than 0 or equal to 0. This time around, it is equal to 0. Now, why we are checking this, you will understand in a bit. Now, we are also taking into consideration that temp should always be, or it should be less than ARR of j. Now, if 5 is less than 10, that means this will be our new sorted array, and in that sorted array or sorted part, this is the unsorted part obviously. Now in that sorted part, 5 should be first, because we are considering the ascending array and we are trying to sort our elements in this array in ascending order. So this should be the scenario. Now this condition holds and this condition also holds. Now what we are doing, we are changing the j plus 1 index, that means we are talking about this index, and we are writing 10 over here with this step. Now you might be thinking, okay, now we have an array in which both of these elements are 10, but we have already stored this in a temporary variable. That is for the same reason we were using this temp variable tmp, just to store that element. Okay, now that is done. But now we are considering in the backward direction. We are trying to sort whatever is in that portion, in that sorted portion, because this will always be the sorted part and this will be the unsorted part. So now we have checked this element and we have swapped them. Not swapped them, we have shifted them, right? We haven't yet changed this temp back, right? We have a new array that is 10 and 10 in this portion, right? And now what we are doing, we are decrementing the j, and now j will be pointing to -1. But now that there is no such element in here, so this condition will not hold, and this should be given as false, right? And now we'll be out of this while loop. Now in the final step, what we are doing, we are now changing this j plus 1, that is this element that is there, that j plus 1 element, which earlier was minus, which now once decrementing it, it is -1. Now what we are doing, we are incrementing it again. That means we are talking about j plus 1, that is -1 plus 1, and this is the index. That means we are talking about ARR of 0. And now what we are doing, we are storing that TMP, which is nothing but 5. So this element, let me just erase it. So this element will be now 5. So now you see how our dots got connected, and this is the array. Now this is only this thing happened only in first iteration. Now what about the second iteration? let me just erase it and let's talk about the second iteration as well. So we have now 5 and 10, and then we have 6 and also we have 20. So these are all the indexes that we have. And this time around, our I is incremented because this is the second iteration. So I will be pointing over here and j will be 1 less than I. That is, j will be here. And in our temp, we are storing this 6, right? So these are the things that happen in these two steps. Now this thing is also done. Now we are again checking if j is greater than 0. Yes, it is. Right now j is 1. So this condition holds. And we are also checking if temp is less than ARR of j. Yes, temp is 6 and it is less than ARR of j. Now what we will be doing, we will be changing the positions or shifting this 10 to this, right? Now here we have 10, right? And this is also 10. Now this is also 10, right? Now after that, what we'll be doing, we'll be decrementing j. Just using the eraser over. Now what we will do, we will just decrement our j, and now this time around j will be on 5. Now that is done. Now again, we are not out of this while loop yet. Now again, we will check, is j greater than or equal to 0? Yes, this condition holds true because right now j is equal to 0. And is temp less than ARR of j? Is 6 less than 5? No, it is not. It will not hold, so it is false. So we are out of this while loop. Now this time around, j is still at 0, right? In the second iteration, j is at 0. Now what we will be doing, we'll be using this last step that is over there. We are just doing j plus 1, that is 0 plus 1. At this index, please store temp. That means ARR of 1. That means we are talking about this position, which was earlier we overwrite it, or we had 10 over there, right? And now we want there to have this 6. So we will overwrite this 10 with 6. So in nutshell, what we will have over this position, in this position we will be having 6 because of this step. So this step is very important, right? So this is the most important step, and this is the one that is responsible for making all those shifts. Okay, so now this happens in the second iteration, and now we have our sorted part, that is 5, 6 and 10, and finally we have at this 20. And the last iteration, nothing will happen because we will be out of this loop because ARR of j, that means this is our I and this is j. This is not less than, 20 is not less than, so nothing will happen. At this time around, this temp will be changed with this 20. So 20 will be changed with 20. So nothing will happen. And at the last step, in the last iteration, we'll have a sorted array that is 5, 6, 10, and 20. Done. Now let's see its implementation. So now if you can see that the IDE that I'm using is code blocks. Okay, so you see this is our display function, which is just displaying the array. That means we are iterating from 0 to n, and we are just printing out the elements in the array. This is our display function. This hash includes studio.h. This is just for implementing the printf and scanf statements, if there are any. Okay, so then we have this insertion sort function, which is similar to what we just saw. So we are starting from I equal to 1 and then to n, and then we have this temporary variable which is storing the element, and then we have this while loop which helps us to make those shifts, and finally the most important step that is over here, which is the exact location of that element which is being shifted, okay, which has to be shifted. And now that we have this main function over here, that is our driver function, in this we are using the static array, that is 95143, and then we are first calculating the size with the help of size of operator, and we are calculating the number of elements in this array. That's it, right? And then we are printing the elements before sorting and calling the display function over here. Then we are calling insertion sort function. Then we are again printing the elements after sorting and with the help of display function. Okay, so now let's save this file, and now let's try to build it and run it at the same time. Now if you see, the elements before sorting were 95143, and after sorting it is 13459, which is obviously sorted. So in this way we implemented insertion sort using C. Now let's talk about insertion sort time complexity. So in the worst case, when all the elements are in haphazard manner and we need to sort them one by one, So obviously we are talking about first the outer loop which runs from 1 to n, and then the inner loop which runs backwards, and in the last, first we consider, in the first iteration we only consider the zeroth element. Then as we move along, it will be running from n to zeroth element, right? We will be considering the whole n elements. So in that case, the time complexity in the worst case will be order of n squares, because we have two nested loops. That is, one is for loop, and inside that for loop we have that while loop, right? So this is the in the worst case, and it happens also in the average case, where some part or the sorted part is already there, and it is, let's suppose we have 5 4 5 6 7 8, and then we have the unsorted part. So half of the elements are sorted and half of the elements are not sorted, so it will be n square by 2. So we are not considering the case where we talk about constants and we are negotiating the constants, and in that case the average time complexity will be n square, right? But the most important thing that is there in this time complexity is the best case. That means when your elements, that is 5 6 7 8 9 and 10, when the elements in the array are already sorted, what happens in this case? If you observe, the for loop that runs from 1 to n will be always there. So n is always there. The time complexity, the big O notation, big O of n will be always there. But in this while loop, wherein we were checking for if j is greater than or equal to 0 and if AR of j is less than 10, right? In that case, this will never be executed, because this AR of j will always be greater than 10. Why? Because we are talking about this element and we are checking if this 6 is less than 5. No, it is not. If this 7 is less than 6, no, it is not. So this condition will always be false for all the elements. So in nutshell, we are just checking these steps only once in every iteration. So that is for the reason that the whole time complexity in the best case will be big O of n and not big O of n square in the best case. Okay. Now let's talk about insertion sort space complexity. If you have observed in algorithms and in implementation, we never talked about any auxiliary memory, right? We were not using any extra space, either in the form of array, linked list, stack, queue, or anything, right? So that is for the reason the space complexity of insertion sort is big O of 1. That is constant amount of space. Now let's talk about insertion sort analysis, wherein we will be analyzing comparisons, number of swaps, stable or unstable, in place or out place. So first let's talk about number of comparisons required. In this we will talk about two scenarios, wherein we will talk about worst case and average case. In worst case, the number of comparisons required is n square by 2. Now, if you talk about average case scenario, it is n square by 4, which is twice as much as this, right? It is 2 times. If you talk about number of swaps that are required in insertion sort, again we will talk about two scenarios, average and worst case. In average case, it is n square by 8, and in worst case, it is n square by 4. These are the number of swaps required. And if you want to check those, if these statements hold or not, if these equations hold or not, you can always take an example wherein you will be considering both the cases, even as well as odd. So take an example and run through it. Now, if you talk about stability of insertion sort, it is a stable algorithm. What do you mean by stable? So if you have an array which contains 1, 3, 1 dash, and 5, in this array, the relative position of these two ones, that is this one and this one, let me change the color and let me show you. The relative positions of this one and this one will remain intact. What do you mean by this thing? That whenever you are sorting it, you can sort it in two different ways, right? This is also sorted and this is also sorted. That means you can either have 1 dash 3 and 5, or you can have 1 dash 1 and 3 and 5. this is obviously that this number is repeated, but this is the first number. This occurred here the first time, and here it is the second occurrence. Now you want to keep their relative positions intact, right? So both of these are sorted, right? But if you talk about stability, this is known as stable and this is unstable. Okay. Now, insertion sort, whenever you are trying to implement insertion sort, it is stable. That means the relative positions of both these ones will be intact. Okay. So if someone asks you if insertion sort is stable or not, you will say yes. Why? Because the relative positions of the numbers that are repeated remains intact. Now, what about this in place or out place? Since we are not using any auxiliary memory, right? We didn't use any stack, queue, linked list, or array. That is the reason that whenever you are not using any extra memory, it is supposed to be in place algorithm. So if an algorithm is sorted within the array that was there earlier, that means you're not using any extra space. That algorithm is known as in place algorithm, which is evident now in insertion sort as we are not using any extra memory. So insertion sort is an in place algorithm. Now let's look at the example wherein we will implement insertion sort. If you can see, we have this example over here wherein we have 6, 5, 3, 2, 8, 10, 9, and 11. And we have been given this key. What this key signifies that the maximum swaps or comparisons needed for this tree, either on the left side or on the right side, right? The number of positions that this tree needs to get to its original position is 3. So this is a question that is known as nearly sorted array or k-sorted array. We do not need to sort all the elements in the array, but we are specifically looking for those elements which are not at its original position. And if we want to get them to their original position, the maximum comparisons or swaps that we require is 3. So if you see this 3, the original position of this 3 is this 5. That means in the sorted array, it will be here. Similarly, if you talk about this 2, the number of swaps that it should do is 1, 2, and then it will be at its original position, or you can say that 1, 2, and 3. So max it can go to 3 positions. Okay. So similarly, it will be the same for all the elements. So at most 3. Okay. And at least it can be that it doesn't need to move at any location, that it will have its own original position. Just like in 11, you see 11 is at its own position in the original array as well as in the swapped array. So at most you have 3 positions. So now if you talk about its implementation, we are going to implement it with the help of insertion sort. Why? Because we know if we are not swapping it, then the time complexity will be reduced from big O of n square. Now there are some elements and the maximum swaps that we are going to do is big O of n into k, okay, to the base 2. So maximum we are going to move, or the internal loop, that is this loop, will work maximum k times. That means what is the value of this k? So that many times this internal while loop will work. Okay. So if we can observe carefully, this is the same implementation of insertion sort that we have seen earlier, right? So we have this array, we have this size, then we have these 3 iterators I, k, and j, wherein this is the outer loop, this is the inner loop, and instead of temp we are using this time around, we are using this variable k. That's it. Okay. So at the end, this is the most important step, which is wherein you are storing that element at its original position. That means, let's suppose you have this 10, 6, and 5. Then this time around, this 5 at the last step, this 5 will be here in this step at its original position. Okay. So we have 5, 6, and 10, because in the meantime, what will happen? The 6 will be replaced with the 6. and this 6 will be replaced with this 10. Then we have this 10 over here, 10 and 6. So in the meantime, we will be having this array 10, 10 and 6. So at last we will be having this 10, 10, 6, but we are missing one important fact, that obviously these two elements should be sorted in when we have moved to this step, this third step. Obviously these two should have been sorted. So this will be 6 and 10, then we have 5. So this will go 10 and 10, this will go here 6 and 6 in the second iteration in this while loop, and finally this step will be there and it will replace this 6 by 5, and this will be your sorted array after in the second iteration. That's it. Okay, so this is the same algorithm or implementation that we have earlier seen in the insertion sort, right? And now let's see its main function or the driver function. That is, here we have this array in which we have all the elements that is nearly sorted or k sorted, and then we calculated the size of the array, and then we have this k. You might be thinking, okay, why we are not using this k if this is given to us? Since this is not the efficient approach, right? This is not the most efficient approach to use the insertion sort, but yes, there is a 50-50% chance that you might get selected if you apply your brains and you use insertion sort, because it is obviously better than n square. That is the most naive approach. You are using something that is better than n square. You're using n into k. Okay, why this n is there? Because you will be iterating through all the elements one by one, and you will be swapping them in the internal loop only k times. So you have this k over here, which is 3, and we will be displaying our elements before they were sorted. And after we apply this insertion sort function, we call this function over here, and then they will be sorted, and we will check with the help of display function. We will implement this display function as well, right? And we will see if our elements are sorted or not. So now if you can see that the IDE that I am using is code blocks, and if you see, we have implemented 3 functions. Now let's see first our main function, that is our driver function. In this, we have this array that is there. Then we calculate the size, we have this k, we have this elements before sorted. Then we are calling display function. Then we are calling insertion sort function. Then we are printing these elements before sorting and after they are sorted. Okay, so this is our main function. And if you talk about insertion function, it is similar to what we have seen earlier. So in this case, we are using this temp variable, not k, and we have this temp as arr of I, and then we are calling these functions. And then what we have inside this for loop, we have this while loop, and then there is this step, the most important step, wherein we are swapping them at the end. This is our insertion sort function. And then finally we have our display function over here, wherein we are just iterating through all the elements one by one. So we have these 3 functions over here. This hash include stdio.h is nothing, but since we are using this printf statements or scanf statements, if we had used any. So if you want this array to be dynamic, right? So the user should enter those elements, then you can use scanf. So you don't have to implement those functions. Those will be included with the help of this library. Now let's save this file. And now let's run this file. Let's build and run, and let's see the output. If you see, the elements before sorting were 6, 5, that is not sorted. And after sorting, we have 2, 3, 5, 6, 8, 9, 10, 11. So this is your implementation. So this is your implementation of this example, which is sorting nearly sorted or k sorted array with the help of insertion sort. I want you to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new updates on video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on this video any queries or suggestions, and I will respond to your comments.